Yeah, I found it for now.
Okay, so then,
No, I haven't said my home.
Why do you mix them?
well, because it said journal entry. I honestly have to.
This is a kind of.
Now that you say that, this is just.
That needs constant TN.
It's only because it's not.
What do you say? Chapter 6, Chapter 7, Chapter 8, done. All right, and now we're moving into Chapter 9. And this is free convection. So let's get going right now. This is a whole fill up every board thing. Did you get my answer?
Yeah, I was confusing volumetric flow rate and mass flow rate.
All righty. Free convection. Well, you know, we've covered this already a little bit. You had an introduction when we did the FinLab. So this is not the first time. And then, of course, more when we did the transient lab as well. But free convection is buoyancy-induced motion. I never spell buoyancy. And it results from a density gradient. Body. Redo this. Body force is acting on the density, but it's the body force itself is gravity. There we go. So it's buoyancy-induced motion resulting from a body force, gravity, acting on density gradients. This sounds very, well, it sounds very scientific, blah, blah, blah. But basically, hot air rises, okay? Cold air falls. You've all been in a restaurant, air conditioning, cold air falls on you, it's uncomfortable. If you come back here by a window on a day like today, you can feel almost an air current from the cooling associated with the air coming in contact with the glass and being cooled. What happens to the density when the air is cooled? Pardon me?
It increases.
It increases, and therefore it becomes heavier than the surrounding air, and it falls down. And that, ladies and gentlemen, is density. Okay? Simply stated. All right? And these density gradients are produced by temperature differences, or gradients. And that's free convection. Now, some examples of free convection. We've already just given you one. Probably you've seen it, HVAC systems, where cool air comes out and falls down. All right. We have walls and windows of buildings. One of my favorite is the this football player who takes his helmet off during the game, and you can see, the little air moving. That is from the air coming in contact with his very hot head and being warmed and then rising, and you see the motion. You also see that same free convection effect. Very hot days on roads. If you've ever been in the desert, you can see the waves of the air rising off the hot surfaces. That's all examples of free convection. So those are biological and natural. HVAC systems where the air comes out of the ducts and falls down, for example. Electrical equipment is another example. When computers first came out, the central processing chips were not very powerful. My first computer had a hard drive, and that was that was really a big deal. And the hard drive was 20 megabytes. 20 megabytes. Not much on there. 20 megabytes. That was the whole hard drive, by the way. So they weren't real big. The processors weren't real big, so they didn't use a lot of electricity. And then as they became more and more powerful, it wasn't enough to have free convection carry away the heat. So they got more sophisticated. I've showed you an example when we did the fins of how they put fins on they attached the chips with the backing of fins so they cool them. And the next thing they did is they put a fan on there to circulate the air. And as you all know from the fin experiment, you typically more than double the heat transfer coefficient when you accelerate the air over the object which is being cooled rather than just allowing it to be cooled by natural or free convection. Okay? So these are all examples. But free convection is an important thing to understand. So we're going to spend the next 2 lessons, including today, trying to understand it. So let's start by looking at laminar free convection laminar free convection on a vertical flat plane. Now just for the just to point out to you, the axis system here is a little different than we've been accustomed to. The vertical direction here is X and U, and the horizontal direction is Y and V. Okay? Y and V. So it's switched our coordinate system by 90 degrees. Now what happens here, if we have a plate, and we'll call this TS, and out here we have what is known as quiescent fluid. Quiescent, if you look it up, means still. Okay? Still. Or not moving. It's the air that's undisturbed. Sometimes I use air, I should be saying fluid, but more often than not, free convection deals with air. So typically it is a quiescent fluid out here, and it's at some temperature T infinity. And what's its velocity?
0.
0. Thank you. Okay? Now, what happens is this Ts is greater than T infinity. So what's going to happen to the air which is adjacent to the vertical flat plate? Abdul? It's going to begin to gradually warm up. And some of those molecules, as they become more energized, their density is going to decrease, And so compared to the molecules around them, what's going to be the tendency for them to do? Begin to rise. Okay? And this is what we're talking about by buoyancy-induced motion resulting from body force acting on a density gradient, which is driven by a temperature gradient. Okay? And what you see forming here is a boundary layer. All right? But some of the things that we have here is a little different. Let's take a look at what the velocity profile looks like. There's our velocity profile. Right here, at the surface, what's the velocity of the fluid? Derek?
0.
0. Why?
Because at the surface the flow over.
Help him out, China.
The fluid that's against the plate is not moving, so.
Why? That's correct.
Friction.
Yes, viscous effects. All right? It's stuck. All right? Over here, what's the velocity of the fluid? Steve? Why? Because that marks the end of the boundary layer. All right? What's happening in the boundary layer? We're having the fluid accelerated because of these temperature gradients and how that acts on the density and gravity, acting on the density differences. But here, that is negligible. So we mark the end of the boundary layer where the velocity of quiescent air or quiescent fluid is once again 0. Okay? All right, so that's what this looks like. All right, so we have Ts greater than T infinity. We have the density out here of the air at some, of the fluid, at some density rho infinity, and as we've already indicated, there's no movement out here. But there is some movement in here. There is some movement. And this is going to be U a function of y. All right, we're going to have a profile in that fashion right there. All right, and of course we have acting
Why is it not X?
because we have changed our coordinate system.
Isn't it a function of x and y? Just in the x direction, it changes the relation to y.
Yeah, it would be a function of x and y, but we always just consider it y. So I'm trying to
Why?
I'm trying to figure out why, because you asked that question. Huh?
So do you,
That's a good question, though.
so do you consider it up there where the boundary layer kind of like a glass cells where you kind of ignore it?
No, you're absolutely right. But I'm gonna figure out. I'll have to get back to you about that. But it does seem reasonable. But I can tell you for a fact that the book does it only as a function of u. Now, in the fully developed version, we can say that's the case. But clearly, the velocity is going to be changing as we move in the boundary layer, in the x direction. So this is going to be the x direction, and it's going to be the y direction. So the profile is going to be the curve at any given point. At any given point, u will be equal. The profile will be a function of y. That'd be one way. But you're right. I think that's probably it. All right. All right. So now we're going to take a look at the conservation of momentum. Before we begin the conservation of momentum, we're going to introduce something called the Boussinesq, and I apologize to anyone who speaks French. Approximation. B-O-U-S-S-I-N-E-S-Q. Boussinesq approximation. And the Boussinesq approximation says that we're going to neglect property variations except for the variable density. In the buoyant, the effective variable density in the buoyancy force. That's known as the Boussinesq approximation. So, for our momentum in the x direction, we have u times the partial of u with respect to x plus v times the partial of u with respect to y. Those are our momentum equations. Is going to be equal to the forces, which is going to be minus 1 over rho times the partial of p with respect to x minus gravity. Gravity is going to be acting down. In this case, normally we don't have gravity acting in the x direction, but we've switched our reference frame 90 degrees, plus nu times the second order partial of u with respect to y. Okay? Pardon me?
Is that V du dy?
No, that's nu.
On the other side.
This is v.
No.
That's v. U times du dx, v times du dy, minus 1 over rho, dp dx, minus g, plus nu times the second order partial of u with respect to y. Okay. Now we're going to evaluate this equation in the Poisson region. Okay, so we're going to evaluate this out here. Now, we know that the air is not moving, so U is going to be equal to V, is going to be equal to 0. So that means this term goes away, and this term goes away. So what we're left with is simply that the change of pressure with respect to x is going to be equal to minus rho infinity times g, because only these two terms will be impacted. And that makes sense. What does it basically say? Yes, Louis.
Is that minus G or times G?
Pardon me? This is
On the top part.
minus g.
Oh,
Says
Okay.
rho g.
Yeah.
Pardon me?
You said, you asked what it basically means, rho g.
Right. It basically means that your pressure is a function of how much your pressure gradient is going to be a function of your density times the acceleration due to gravity, which we kind of know. All right? So we're going to rewrite this as minus 1 over rho dp we're going to write dp dx equal to minus rho infinity times g over rho. So we've divided now both sides by rho. Okay? Now we're going to take one more step. Now the pressure must be the same. In both the boundary layer region formed by the movement of the air, as well as the Poisson region at any particular spot. What would happen if it wasn't?
There would be motion.
There would be motion. So, in terms of the vertical axis, at any given point, the pressure gradient has got to be the same. So, the pressure must be the same in the boundary. Must be the same in the boundary layer as in the Poisson region. So, we're going to say that u, partial of u with respect to x, plus v, partial of u with respect to y, is going to be equal to, now we're going to make a substitution, g over rho from this, times rho infinity minus rho plus nu times the second order partial of y, excuse me, second order partial of u with respect to y. And this is nothing more than the momentum equation substituted with this relationship here in for this term. And this applies to the boundary layer. Yes, James? Yeah, we'll go down here. Well, one of them should certainly be positive. This makes sense. They're both negative here. So this is right, and then this has got to be right. Yeah. Okay. Very good. Thank you. Okay. And then, if the world is right, we should be able to substitute in for this. This turns out to be this. So that's g times, that's correct. Thank you. Okay? So this is equation 9.3, by the way, in your textbook. Alrighty? Yes, Nick.
Is that G over rho or G over P?
This is G over rho.
Okay.
This is the rho, by the way, and this is kind of an important distinction. This is the variable rho. Alright? So we allow that variable rho to change, which it will in the boundary layer, where rho infinity designates the density of the Poisson fluid. Okay? Alright. Okay. Anybody want to wager a guess or an intelligent estimate of what that term right there physically represents? Dylan, is that you? You're absolutely right. This is our buoyancy force.
Archimedes principle, right?
Yep. And that is your buoyancy force. And that is what's going to be counteracting and moving the fluid. Very good. All right, now, and this is valid, this expression as written right here is valid everywhere in the boundary layer. Okay. Now, before we go any further, we want to introduce a new term. And this is in your homework tonight. And this is the volumetric thermal expansion coefficient. The volumetric thermal expansion coefficient. Now you're familiar with beta already. As a matter of fact, some of you became painfully familiar with beta in your fin experiment when beta was used it for air and you used Celsius rather than Kelvin. Calculated. Okay? So that's one example. What is beta? Well, from Maxwell's equations in thermodynamics, which we did not cover here, there are a bunch of theoretical relationships. Beta is defined as the minus 1 over rho times the partial of pressure, the partial of rho with respect to temperature holding pressure constant. Now, this is important for you for another reason right now, and that is for your homework problem number 2, the homework I just passed out. You're going to approximate this partial differential as P infinity, or you're going to approximate this as a difference. For the purposes of beta, as far as the buoyancy over there is concerned, we're going to be looking at the difference between the temperature and the density of the quiescent fluid and the temperature and the density of the fluid in the boundary layer. Tonight for your homework, what you're going to do is, and I'm giving it away, but that's okay, is you're simply going to be looking in the tables and selecting the differences on either side of the temperature that you're given from the table, and you're going to create a difference in density and a difference in temperature, and to calculate this.
Is that
Is that what?
that's pressure, not rho?
This is pressure here. This is the partial density with respect to temperature holding pressure constant. Okay? That's the theoretical Maxwellian definition of beta. Yes?
How do we take the difference in pros of variable as far as what
Well, what you're going to do is you're going to say, okay, 300. So you're going to look at 305, and you're going to look at 295. Okay? So you're going to bracket it. Density and temperature. Okay? All right. All right. Therefore, if we rearrange this, we have rho infinity minus rho is equal to rho times beta times T minus T infinity. Now, for an ideal gas, you can look up beta as a property for most liquids. For an ideal gas, we typically we just use beta, which is equal to 1 over the temperature, and we make sure that the temperature is expressed in Kelvin. Okay? All right, now let's take a look at the governing equations. Remember, as in previous cases, we're dealing with laminar free convection on a vertical flat plate. First equation we have is continuity.
So to get from that last step to the 1 over 2, you just did the ideal gas law.
Pardon me?
How did you get from there to that last step? To get 1 over 2?
I'm not sure. No, I don't, I mean,
It looks like the ideal gas law.
well, it may be, it may be, that would make sense, but you gotta be careful because you can't just, what they've done here in your book in 9.9 is they have used the definition of beta, and then they've, which is the partial of density with respect to temperature at constant pressure. So, if you use the ideal gas law, then you'd express it in terms of pressure, so it'd be P is equal to rho RT, all right? So then rho, hang on a second now, so you want to express rho would be equal to P over RT, pressure's constant, R is constant. You're going to take the derivative of that with respect to temperature. So that would be what is pressure? No, it's pressure times rho. You got me now. You get me. Okay. So you got beta is equal to minus 1 over rho times the partial with respect the partial of P, or partial of rho with respect to P over P. If we say rho is equal to P over RT, then the partial of rho with respect to P, holding pressure constant, or pressure is equal to a constant, is going to be you've got, pardon me? T is the minus 1. 1, so it's going to be T minus 2 over minus 1. No. If you do the, yes, minus 1. So, okay, well, yeah, that's what you're going to do. And is that what's done in the book? Yeah. And then you plug it back in and you should be able to come over 1 over T. That's it. I mean, I've never done that. I always accepted that beta was 1 over T for an ideal gas. So, that would have been a good homework problem. It would have been easy. And then, and so forth. Okay? Yeah, but that's exactly where it came from. Patrick,
So the beta above is.
I get you guys thinking really good stuff here. That's good, that's good, that's good, that's good. I like it. Go ahead, Patrick.
So for the beta above, to calculate that, is that for a non-ideal gas? Or is that just for?
Well, this relationship right here, would be that it's derived from Maxwell's equations. All right, and that would be for any material. But we have to have a way of expressing rho as a function of temperature. That's not as clear for a non-ideal gas. Okay, although there are some relationships out there, like the van der Waals equation and things like this.
Oh my gosh, yeah.
Pardon me?
I said, yeah, those.
Yeah, but they wouldn't be as simple as this. What's typically done is that these things have been empirically and they've been experimentally determined, like the steam tables. Okay? And there's a whole science to that, by the way. Frankly, it's beyond the scope of the course. It's really interesting stuff if you ever want to, I mean, well, you got to be pretty into this stuff. But I mean, if you, there's a whole book on the steam tables, on how the steam tables came about, and how they did this stuff, and, came up with the different values for enthalpy and things like this. Kind of interesting. Combination of science and experimentation. I haven't. I can honestly say that I've looked at it. Keene and Kay's development of steam tables back in the early 1900s. Kind of neat stuff. Yeah, I couldn't focus. Have I read them all? No. I was thinking the other day, if I retire, I could read all these old books. All right. So this definition holds for everything, but this result is only for an ideal gas. And the short answer to your question. All right. Continuity. Any other questions? That's a good question. I like it all. All right. Continuity equation. Partial of u with respect to x plus the partial of b with respect to y is equal to 0. We've seen that now a lot. Now this is equation 9(6).
Still in the Westian region, or is this?
Now it's just, we're going to apply them, but for right now, this is just the general governing equations for fluid. We're going to apply these in the boundary. We're going to apply them in the boundary layer. But for right now, just leave them as they are right here. Momentum. And this is in the x direction, and that is u, partial of u with respect to x, plus v, partial of u with respect to y, is equal to g over, or g times beta times t minus t infinity. Okay, so that comes from this right here, where the rows cancel out. We're left with g beta times the temperature difference plus nu second order partial, nu times the second order partial of u with respect to y. This is equation 9(7). Okay, and what this basically says is that this is the change in momentum these two terms here would be equal to the sum of the forces, and those forces are the buoyancy force and this is your buoyancy force, And what does this represent?
Viscous forces?
Megan?
Viscous forces?
Very good. The viscous forces. And what do they do to each other?
Cancel each
They
other.
can't, they oppose each other.
Yeah.
The viscous force is going to resist the movement of the fluid molecules, and the buoyancy force is going to aid the movement of the fluid molecules. Okay, very good, very good. All right, and then lastly, energy equation. And that is U times the partial of T with respect to X plus V times the partial of T with respect to Y is equal to alpha times the second order partial of T with respect to Y. And this is equation 9-8. And we're out of time for today. So that's okay. We're gonna take a look at this and complete this next time. I will point out to you that your homework, what we're in right now is section 9.2 of your textbook, and I believe in your homework, I actually reference